We are now covering the solutions to quiz number 2. A boy wishes to row across a river in a boat. The water flows with a uniform velocity, shown by the vector g in the figure. The possible velocities at which the boy can row his boat are shown by the vectors at the right. The velocity vectors are drawn to scale, which line on the graph with each line on the graph representing 0.1 meters per second. Okay, in which direction, A to H, should the boy row in order to cross the river in the shortest time? Okay, now to cross the river, you want to go from left to right. You go from here to there. Okay, so the x direction only matters, so you just need to have the biggest possible value for the x component. So that's clear which one that is. You simply want to take the vector c, which has the biggest x component. Okay. Now, next problem. In which direction should the boy row in order to land on the opposite shore directly across from the starting position, either upstream or downstream? So in this case, we want v boat, which is the sum of v river plus the velocity of the boat relative to the river. We want v boat to point in the plus x direction. This means that v boat y component needs to be 0. We know that v river y component, the y component of the river velocity is 2 blocks up, so that's 0.2 meters per second. Therefore, we need the y component of the boat relative to the river to be minus 0.2 meters per second. So we need something to go have negative 2, so that's h has negative 0.2 in the y direction, so the answer is h. Number 3, you are a medieval knight attacking a tyrant's castle with a cannon. The ball leaves the cannon with a speed of 32.7 meters per second. Okay, they tell you h here is 0. The angle is 39.1 degrees. What is the time of flight of the cannonball? Okay, first step is we get the components of the cannonball. The initial components of, the initial velocity components. So we have v0 was 32.7. The x component is the cosine of 39.1 times 32.7. Cosine b is the adjacent side. Okay, and then we have the y component being 32.7 times the sine of 39.1. So the x component initial becomes 25.4. 25.4. The y component becomes 20.6 meters per second. Okay, so now the ball goes up, the cannonball goes up and it goes down. The height is exactly 0. So the time is determined by the y motion. Y minus y0 is equal to, we're going to find delta t. So y minus y0 is 1/2 ay. Delta t squared is v0y delta t. Okay, because in the y direction, ay is negative 9.8 meters per second squared. And so we have 0 is, because it starts from the ground and it ends at the ground, y minus y0 is 0. We have 1/2 ay, which is negative 9.80, and delta t squared, plus the initial velocity y component. We calculated that to be 20.6 times delta t. So now there's a delta t, there's a 0 here, so we can just divide by delta t, and then it becomes a linear equation of delta t. So we have minus 4.90 delta t plus 20.6 is equal to 0. We can solve for delta t. It's 4.20 seconds. Number 4, a rescue airplane is flying in the horizontal direction with a speed of 924 kilometers per hour at a height of 479 meters to drop food to 2 started hikers. How far ahead should the pilot release the care package straight down so that it lands right next to the hikers? Okay, so the time of the flight, well, the time of the drop will be determined by the y motion because there's a set distance it needs to drop. Okay, now let's first get the components of the velocity. These are relatively easy. The plane is going horizontally, so v0x is equal to just plain v0, which is 724 kilometers per hour. We should convert this to meters per second, though. Kilometers is 1,000 meters. Hours is 3,600 seconds, so we get 257 meters per second. The y component is 0 because it's horizontal. So now I said the time is determined by the y motion. Y minus y0 is equal to 1/2 ay delta t squared plus v0y delta t, but v0y is 0. It's horizontal. So now it's going to drop by 479 meters, so y minus y0 is negative 479. So we get ay is negative 9.80, and then we're solving for delta t squared. This term has vanished. So we get that delta t is 9.89 seconds. Now we look at the x direction and say we know delta t, let's calculate x. There's no acceleration in the x direction. So x minus x0 is v0x times delta t. So that's 257 for the v0x that we calculated here. We converted from the units from 929 kilometers per hour. And then we had 9.89 for delta t from here. And we get 2,540 meters. That's how far it travels horizontally. Okay, so a bicycle is moving with a speed of 3.34 meters per second. The radius is 0.450 meters. How long does it take for the wheel to make one complete revolution? So omega, the angular velocity, is equal to v over capital R. So that's 3.34 divided by 0.450. That's 7.42 radians per second. To get the period, it's 2 pi over omega. So we have 6.28 divided by 7.42. That comes out to 0.846 seconds. Number 6, the flywheel of an engine begins to rotate from rest with a constant angular acceleration of 1.40 radians per second squared. It accelerates for 33 seconds, then maintains a constant angular velocity. Calculate the total angle through which the wheel has turned 46 seconds after it begins rotating. Okay, so there are two stages. First of all, the first stage we have uniform constant angular acceleration. Second stage we have constant angular velocity. Okay, for the first 33 seconds we have delta theta, let's call it delta theta 1, is 1/2 alpha delta t squared plus omega 0 delta t. But the initial angular velocity is 0, so we can cross this part out. And we get 1/2 1.40 for alpha times 33 is delta t, so 33 squared. And that comes out to 762 radians. Now omega, we're going to need to know what omega is for the second part. So omega, the final angular velocity after the first stage, will be alpha times delta t, because it starts from rest. Okay, so we have alpha is 1.40 times the time is 33. That comes to 46.2 radians per second. Now in the second stage, we have, it's a total of 46 seconds, so minus 33 seconds gives 13 seconds in the second stage. So delta theta 2 is going to be just omega 0, the initial velocity, which is this value, 46.2, times delta t, which is 13. That comes to 601 radians. So we add these two together, 762 plus 601 gives 1,363 radians total. Next problem. Number 7. A car is exiting the highway. It's on a circular exit ramp traveling with constant speed. Okay. Speed is constant when the car is at point X on the ramp. Which vector represents the direction of the car's acceleration? So we have uniform circular motion. It just points straight towards the center of the circle. Okay, so that will be the vector H. Centrifugal acceleration. There's no tangential acceleration because the speed is constant. Now, when the car is at point Y on the ramp, it hits a smooth ice patch. Which vector represents the direction of the car's velocity while the car is on the ice patch? Okay, so at this point, it's just the velocity is going tangent to this circle. If it becomes icy here, it just keeps going in a straight line. So V just goes straight like this, which is in the G direction. Okay, let's go on. Number 9, a force accelerates a car with mass 1,200 kilograms at 3.01 meters per second squared. What is the force? Okay, F net is equal to ma. M is 1,200, A is 3.01. Multiply them together, you get 3,612. Next problem, number 10, last one. we have two forces. F1 is x component minus 5.50, y component 4.00. F2, x component is 5.90, y component is 3.20. It's acting on a mass 3.10 kilograms. And what is the magnitude of the object's acceleration? Okay, first get the net force, F1 plus F2. Add the x components together, minus 5.50 plus 5.90. 4.0 plus 3.20 for the y components. We get 0.40 for the x components. We get 7.2 for the y components. We get the magnitude of the net force, sum of the squares, take the square root of the sum of squares. You get 0.40 squared plus 7.20 squared. Take the square root, you get 7.2 newtons. Now F net magnitude is equal to MA magnitude, so A magnitude is F net magnitude over M, and that's 7.2 divided by 3.10, the mass, and that comes out to 2.33 meters per second squared.